Hi and welcome to this section where we're going to look at a very powerful technique for solving equations numerically, which is the Raphson method, or commonly known as the Newton method. Now, we have a diagrammatic illustration here which we are going to use. Okay, so the method is quite simple it's quite simple and yet very powerful. So this is how it flows. We consider a function. We consider our function f of x equals to 0. Okay, and where f has a continuous derivative. Okay, so we have a function here and it has a continuous derivative f prime of x. Okay, so if we come here, okay, we can see that at x equals to a, we can say that f of x, which is equals to f of a, equals to 0, because it is cutting here. It is at the x-axis. It is on the x-axis. This point x equals to a is on the x-axis, and therefore we say that a is the root of this equation f of x equals to 0. So what we want is to move. If we start with an approximation here with x naught, which is a distance from the root, far away from the root, okay, from the desired root. This is our desired root, and then we are starting here at x naught equals to b. So what we want to do is to move with successive approximations, x1, x2, x3, and so on. With successive approximations, we make sure that we move closer and closer to the root. Okay, so also here on the diagram, we can make use of this illustration here and say that if we start with an arbitrary point x naught, okay, we see that the tangent to the curve f at the point here, this one here, at the point x naught and f of x naught, the tangent to the curve at this point here, okay, meets the x-axis, okay, or touches the x-axis at the point x1 here. And from that, from our calculus, we know, or we can see that the tangent of this angle here beta, with which the tangent of this angle here beta, okay, also describes, okay, the slope of the function at the point x naught, okay, at this point here, x naught, f of x naught, okay. And we know that we can get this by getting the change, okay, in the horizontal, no, the change in the vertical axis, which is f of x naught here, and then here, of course, this is going to be f of what? I mean, this is x. Let me write it in a different color. This here we have x1, f of x1, okay. So the change in the vertical axis, which is f of x naught minus f of x1 divided by the change in the horizontal, which is x naught minus x1, okay. Good. Now, as f of x1 approaches 0, okay, as f of x1 approaches 0, then we can approximate this by writing f dash x naught will equal to f of x naught divided by x naught minus x1. Okay, and then we can rearrange to make x1 the subject here by saying that x1, okay, x1, okay, how can we do this? Okay, let's just say minus x naught. Oh, what am I writing? Let's say x naught minus x1 equals to minus f dash x naught plus f of x naught. Okay, and then we can say, oh, what did I write here? This, we write this comes here, and then this is going to be f of x naught divided by f dash of x naught. Okay, and then we can make x1 the subject, and then we write it as x naught, okay, minus f of x naught over f dash of x naught. Okay, so if we kind of repeat this same principle here, or reasoning we have used, then we should be able to see that we come up with x2 as x1 minus f of x1, f dash of x1, and so on and so on. So with and xtd equals to, then you just update xtd equals to x2, 2 and 2, such that in general we can write that if we want to find the next approximation here, xn plus 1, we can approximate it by taking xn minus f of xn divided by the derivative of the function at the point xn. Okay, so that is it. That is just the idea behind the Newton-Raphson method here. Okay, so it is quite as simple as this, and yet very, very powerful. So if we are going to write the algorithm here, we are simply interested in finding, okay, we have the function, then we compute its derivative. I think that's the major thing in there. We just get the derivative and then we implement that. Okay, let's look at a simple example here. Which example can we look at? We want to look at, let us find an approximation of root 5 to 10 decimal places. Okay, root 5 to 10 decimal places. Okay, so say that let x equals to root 5, and then when you square both sides, you're going to say that x equals to 5, and then we can rearrange this to say x minus 5 equals to 0, and then we can say that this is going, we can write it in the form f of x equals to 0, where f of x equals to x squared minus 5. So we can use the Newton-Raphson method. We can start with an initial guess. Maybe let us say what guess? Okay, before we start with an initial guess, what does the Newton-Raphson method tell us? That if we want to get the root, we shall get this minus f of xn divided by the derivative. Okay, so we have f of x. What is f of x? X squared minus 5. And then what is the derivative? F dash of xn. So this is xn, and then this one here is going to be 2xn. Okay, so we shall just substitute that, and yeah, it will be good if you can, as usual, make use of a table. Okay, make use of a table. Okay, okay, so in this table we can have n. What else do we need? Xn. Do we need xn? So we have n. Oh yeah, I think we need xn, because are we going to compute f of xn, and then okay, we can have that, and then we can have okay, what can we have now? We can have, okay, we write xn minus f of xn divided by f dash of xn. Okay, just this, and this is the root. Okay, this is not that neat. You get the idea, right? So okay, let us just compute xn plus 1, where we know that xn plus 1 equals to xn minus f of xn divided by f dash of xn, and then let us compute the error here. You know, the error, absolute value of xn plus 1 minus xn. So you just keep on filling in. Maybe when n is 0, the initial approximation, e.g. we can say that let x naught equal to maybe 1, then we can start with 1, then you find f of 1. F of 1 is going to be, you fill it in here, 1 minus 5, which is negative 4. Then f dash of xn, then we substitute in here the derivative function is 2xn, so it is 2 times 1, which is 2. Then you compute this part here, xn minus f of xn minus f of xn divided by f dash of xn. You compute and fill it in here, and then you can get the error. Okay, the value here, xn plus 1 minus the xn we have here, then you compute the error. So we continue like that, and so on and so on, of course, and then update. Okay, and then update. So when n is 1, now this is going to be x1. Remember, when n was 0, this was x0, and this was xn plus 1 was x1. So when n is 1, what do you have here? Xn is x1, which x1 you already have here. So you just carry the root, this one, you go drop it here, and then compute the rest. And for then this you go to drop it here, update, and continue the rest. As usual, I am not the best when it comes to writing this pen and paper, because I make lots of errors, but the examples are in the book, so I would expect you to take some time and just compute these at least up to maybe the 5th iteration step. Okay, just compute just to get the feeling of how it is done. As usual, I have something here very crude which I wrote down to try to help us understand some of these things or compare. Okay, okay, maybe I should first show you. Okay, so yes, sorry, I should have made this okay quite large. I'm not sure if you can be able to see it. Okay, I think that's okay, and that's okay. So I think this in our Newton Raphson .py, again it is Python, but remember you can we will write all this in MATLAB. The idea is the same, it's just the language which changes. So I have okay, I can write what I have, which we have used in the book, which is the initial root or initial guess, which is 1. And then we define f of x to be a function which returns x squared minus 5. This one is what we are using for finding the square root of 5. And then we define the derivative function, which will form to be 2 times xn, which is 2 times x. And then the count, you have seen this numerous times. Okay, I'm just trying to take count of how many iteration steps we are making. And then I first state a large error because I have to use it somewhere. Error as 1, and then we state the tolerance here to be a given number. Oh, they said to 10 decimal places, so you find a way of trying to change some of these to 10 decimal places. Okay, you can think about it and then see how you can implement it to 10 decimal places. So I will assume that I'm just using here a tolerance of 10 to the power negative 4. And then this, you have seen it countless times, that while the error is greater than the tolerance, then I compute xn plus 1 equals to xn minus f of xn divided by f dash of xn. This is just exactly what we are writing. And then we get the error by getting x1 minus x0, and then we get the count. Okay, I'll write the count, and then if the error is still bigger than the tolerance, then we are going to the next step. And if we are going to the next step, then we need to update. Okay, so our xn, okay, our xn now, is it xn? Yes, at the next step, is it xn or it is xn plus 1? Yes, at the next step now, our xn, which is x0 here, becomes the previous value we got. Okay, so we update, and then and then this one here is just printing to follow up whatever we have here. So we can try to run this, and then we see what we have. Okay, and then we see what we have. Oh, I'm not sure whether you can see this clearly. Sorry, usually I set this before recording the video to have, so that you can be able to see it, but I don't know. Okay, 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 I can change this. Yep, I think you should be able to see that now clearly. Okay, all right, I'll do that. Okay, what did I write? Okay, so I'll do that. Oh, and then we'll write. Okay, it converges quite faster, but you can always check also in the book or in the notes, and we have the root as 2.236, something of that sort. Okay, yeah. And then another quick example, you can take some time and you check with what is the notes that are in the book. And then the other is where we wanted to find the root of the function. Yes, the root of the zeros of the equation x minus cos x equals to 0. It is x minus cos x equals to 0. So here we define the derivative function. You differentiate x, you get 1. You differentiate cos x, you get negative cos x, we have plus sine x. Okay, then the rest is the same procedure. We are just updating everything here. There's nothing that is changing. The only thing that changes is that maybe your initial root, initial guess, and then the function you're using, and definitely its derivative, and then the rest is the same. Okay, so we can run that. The example, also that example is in the book, you can always check it out. And okay, and then you run it, and then you find that yes, iteration count, and then the root, and then the error, iteration count, the root, and then the error. So you check, and then you find that whatever we have here is the same. Okay, only that in the notes you try with pen and paper, and then we find a way of writing also these in MATLAB. Okay, yeah. So thank you, and see you in the next video.